For the second part of this talk, we'll do random walk, as I told you earlier. So, random walk is also in the joking parlance, we say it is the way a person who is drunk walks. Okay. So let me, because we call it a person who is drunk, let me call the person Johnny Walker. Okay. So Johnny Walker decides to take a step to the left, so from k to k minus 1, or a step to the right from k to k plus 1 with probability half each, and does this every time independent of what he had done in the previous step. Okay. And let's say on this line, 0 represents the bar where Johnny Walker had his drink and now is walking, and n is his home. Okay. And the way we think of this is that if Johnny Walker reaches the bar before he reaches home, then at the bar he starts drinking again, and so he gets stuck there. And if Johnny Walker reaches home before the bar, then he goes and sleeps and he doesn't drink anymore. Okay. So now starting from k, what is the probability that starting from k, Johnny Walker reaches home, which is n, before the bar, which is 0. Let me call that pk. We want to first calculate this and see how we can use electrical networks and other things for this study. Okay. Oops. No, I'm going. So to obtain pk, what we do is, so remember, pk is starting at k, reaching n before 0. N was home and 0 is the bar. What do we have? We have some further boundary conditions, namely, if you are at 0, namely, if Johnny Walker starts at 0, of course, he is at 0. And so he cannot be at home before the bar. So probability of reaching home before reaching the bar is 0, if he starts at 0. Remember, k is a starting point. And if he is at home to start with, then of course he's at home and he doesn't go to the bar. Okay. And also, pk, when the Johnny Walker is at k, there's probability half that he takes a step to the left, in which case he is at k minus 1. And from there, it's probability pk minus 1 that he reaches home before the bar. And on the other hand, it's probability half that he goes to the right, in which case is at location k plus 1. And from there, the probability is pk plus 1, because he's starting at k plus 1 now, of reaching home before the bar, reaching n before 0. To make this more precise, you have to do a conditioning argument, namely condition starting at k, condition that the first step is to the left, times probability that the first step to the left, plus starting at k, the first step is to the right, times probability the first step is to the right, and the probability the first step is to the left is half, and similarly this is half, and this is, then that's where pk minus 1 and pk plus 1 comes. So what we have in mathematical parlance is called a difference equation, with the boundary condition given by this blue line, p0 equal to 0 and pn equal to 1. So we want to solve this boundary condition as this difference equation. There's nothing special about walking on a line. In general, you can do on a connected graph. On a connected graph, you pick out two vertices, call one alpha and one beta. So alpha can represent the bar and beta can represent home. Earlier, alpha was 0 and beta was n on the line. And for the next step, the random walk chooses with equal probability among its adjacent vertices. So if on a random graph, there are some adjacent vertices. So if there are 3 adjacent vertices, it takes a step with 1/3 probability to any one of them. And then again, we have the same probability. So Pu is the probability starting at u, reaching beta before alpha. And just like earlier, we can write Pu by conditioning that look at the denominator here tells you the number of adjacent vertices. So suppose there are k adjacent vertices. It takes a probability 1 over k to an adjacent vertex. Let's say the adjacent vertex is v, and from there the probability of going to beta before alpha is exactly p of v. And we have to sum over all possible adjacent vertices, just like I had done earlier, where I summed over the two adjacent vertices, namely k minus 1 and k plus 1. Okay. And again here we have that p of alpha starting from alpha. It is 0 because already at alpha, so you cannot reach beta before alpha. And starting from beta, because you're already at beta, therefore the probability of reaching beta before alpha is 1. Okay. So let's get back to electrical networks and give some notations and definitions. So Rxy is the resistance between two vertices x and y. It's the effective resistance between two vertices x and y. Then the conductance in electrical engineering, the terminology Cxy is the conductance between x and y, which is the reciprocal of the effective resistance. And the conductance of a particular vertex x is the sum over all the conductances between x and any adjacent vertex of x. So this is the conductance of a vertex x. What Ohm's law says is that the current flowing from x to y, which I denote by Ixy, is given by the difference of the voltages between x and y divided by the resistance of xy. And 1 over Rxy is exactly the conductance of that edge xy. And so we can write Ixy as Vx minus Vy multiplied by Cxy. So where Vx, as I said, is the voltage at x, Vy is the voltage at y. Okay. And Kirchhoffs law says that at any interior point of the circuit, at any interior point, not at a boundary point. So in our circuits, which we looked for the grid, the boundary points would be at the origin and at the boundary of the entire box. Okay. So at any interior point, the incoming current equals the outflowing current, and therefore summation of Ixy equals 0. That's what Kirchhoffs law says. By the way, I don't know whether Germans, I think, call it Kirchhoff, but when we were students, we used to always call it Kirchhoff. So let me just stick to Kirchhoff. Okay. So Kirchhoffs law, together with Ohm's law, now gives, just see this, Ixy equals this quantity, and sum of Ixy equals 0. Therefore, sum of Ixy with y adjacent to x of this quantity, which was Ixy, equals 0. Or in other words, because this sum is only over y, so there's nothing special about Vx. Vx can come out of the sum to give me Vx times summation Cxy, which is exactly Cx. So Vx times Cx equals summation Vy Cxy, or bringing Cx down back here, we have Vx equal to this summation of Vy Cxy divided by Cx. I hope this is clear to you, because the summation of Cxy over y is nothing but Cx. That was the conductance of a vertex x. Clearly, when Rxy equal to R for all xy adjacent, sorry, the spelling mistake here. So, because that's exactly what we had in electrical networks. All the resistors were of R ohms. Then 1 over Rxy is 1 over R, and therefore summation over Cxy, which is Cx, is nothing but summation of R over all the adjacent vertices of x. Therefore, Cxy over Cx becomes this ratio 1 over the adjacent vertices of x. Therefore, if I look at the earlier equation, Vx equal to this sum, we can rewrite it as Vx equals the sum over because we have the Cxy over Cx is this ratio. So we have Cxy over Cx here equals 1 over the number of adjacent vertices of x multiplied by sum over the y and adjacent vertex of Vy. And also, since we have applied the electricity to these two boundary points, alpha and beta, therefore, and suppose that the power source is 1 volt, therefore V alpha, the voltage at alpha is 0, and V beta, the voltage at beta is 1. Now see these two equations. These are very similar to these two equations. Instead of V, I have P here. Pu is 1 over the number of adjacent vertices times this sum, and the boundary conditions were P alpha equal to 0, P beta equal to 1. And that's exactly what we have here. Instead of P, we have V. So they must have the same solution. That's exactly what I write here. They are the same equations when we are studying this, and therefore they must have the same solutions. Moreover, at the end point beta of the circuit, Kirchhoffs law says that I beta, the current flowing into the system, is given by I beta equal to sum of y, the adjacent to beta, I beta y. That's exactly what I told you earlier. But then again, rewriting I beta y as we did earlier, then we have V beta minus Vy times the conductance C beta y. But because the solutions are the same, therefore V beta must equal P beta. Therefore, I can replace V beta by P beta and Vy by Py to get this quantity. Now I know that P beta equals 1. Therefore, P beta times C beta y is nothing but 1 times C beta y, which is the sum which comes out. And then the next term is the negative part, which comes out Py times C beta y over. And now I just put in a C beta times C beta here, because this sum is nothing but C beta. So if I take out the C beta, I get 1 minus summation Py C beta y over C beta. If I write P beta y as C beta y by C beta, which is this quantity, but we already saw that this ratio is nothing but 1 over the number of adjacent vertices of beta. This we saw here. Cxy over Cx is then 1 over the number of adjacent vertices of x. So I get P beta y is this quantity. In other words, what we get from this previous equation, I beta equal to this term, is exactly I beta equal to C beta 1 minus summation Py P beta y, because we had, this is the ratio P beta, C beta y by C beta. That is exactly what we had here in the last term on the previous page. In other words, if I bring this to the left, I have summation Py P beta y, sum over all vertices adjacent to beta, equals 1 minus I beta over C beta, because C beta goes here and then it becomes 1 minus I beta over C beta. So we have to understand this term, Py times P beta y, and that's what we want to do now. Remember, P beta y is nothing but 1 over the number of adjacent vertices of beta. This is exactly what we got here. Okay. This is the probability of taking a step from beta to its adjacent vertex y. Because if there are k adjacent vertices, this is just 1 over k. Was the probability of taking the first and for one step. And Py, if you remember, is the probability that starting at y, you return to beta before hitting alpha, before going to alpha. This is the Py. So in this term, Py, P beta y, P beta y, in case a vertex has only k many adjacent edges, this is 1 over k, and Py is the probability which we started with this lecture, namely starting from y, returning to beta before hitting alpha. So now we are nearly in the slog overs of this game. And so for the lattice grid, let's see what we have. Summation Py, P beta y, which we did here, summation Py, P beta y is 1 minus this IB over beta over C beta. I beta is nothing but 1 over the resistance rho n in the grid, and C beta, I just put it back here. And this says, you can see this, that this goes to 1 if d equal to 1 or 2, because if d equal to 1 or 2, then rho n is infinity, as we saw earlier, and equals p, some quantity which is less than 1 if d is bigger than or equal to 3, because rho n is less than infinity. Is some in what we got was rho n was less than or equal to r, where r was each of the resistors, size of the resistors. So what does this say? Therefore, sorry, what does this say? This says that if you start from, let's say, the origin, the probability of returning to the origin is 1 if you're walking in either 1 dimension, which is a line, or in 2 dimension. And starting from the origin, there's a positive probability, which is 1 minus p, that you never return to the origin. Okay. So in 3 dimensions, you can escape. Starting from the origin, you can escape it to a positive probability. It's a positive probability. It's not probability 1. But in 2 or 1 dimension, if you start from 0, the origin, you return to the origin with probability 1. And because you return to the origin for the first time, again after that, you will also return to the origin. So you'll actually return to the origin infinitely often. That's something which can be generalized from this argument, because once you return to 1, it's as if you're starting afresh. But here, that's not the case, because if you return to 1, your probability of returning to 1 is p, which is less than 1. Probability of returning to 1 twice for the second time is p squared, etc. In other words, probability of returning to origin n times is p to the power n, and that goes to 0 as n goes to infinity, because p is less than 1. And therefore, starting from the origin, you return to the origin infinitely often is 0 if you are in dimension 3 or more. So that is the main result of Polyi 1928, that a random walk, what he says is recurrent. That means you start from the origin, you return to the origin infinitely often if you are in dimension 1 or 2, and the random walk is transient. That means you can escape with a positive probability, in which case here it is 1 minus p. Okay. Now I'm going to talk about something which is a bit more modern, and it's the interest of the research community here now, is that suppose we place resistances randomly on a grid. What do I mean by this? Because as I told you earlier, whenever we say random, this is my first lecture, when we talked about the Bertrand's paradox, we have to specify our problem completely. So, okay, suppose we take the integer lattice, 0 n to the power d, with the top and bottom edges shorted, so that we make a cylinder out of it and connect it to a power source. Okay. At every edge, we place either with probability p a resistor of R ohms, or with probability 1 minus p, we remove the edge. So in other words, sorry. In other words, at edge E, we either place, so the resistance of the edge E is either R with probability P, or we remove the edge, means that it's infinity because there is no wire between them, with probability 1 minus P, where R is the resistance at edge E. So let us see the picture. So I have joined the top and the bottom of this grid with a battery source, and each edge here, I've either put in a resistor or I've just removed the edge. So for example, here, this one edge, I have put a resistor here, and I've removed this here, etc. Another edge, I'm putting the resistor here, and totally finally we'll get something like this. We have put some resistors and we removed it. So each red edge is a resistor, and so what we've got is a random circuit. Okay, now instead of 0n to the power d, I made it minus n to the power d, but that is not important, but just a typo. But just take it to be minus n to the d. The question now is, let R and D be the effective resistance of the d-dimensional resistor. What can we say about R and D? What we can show is that for d equal to 2, probability of Rn going to infinity for 2 dimensions as n goes to infinity is 1 if p is less than half, and it's 0 if p is bigger than half. In other words, if the probability of putting an if p is bigger than half, the probability that the resistance, equivalent resistance, goes to infinity is 0. Otherwise, it's 1. And in d bigger than or equal to 3, we get that there exists some constant Pc of d, which we do not know about, such that a similar result holds. And as an exercise, okay, sorry, one more thing. And we also know that the effective resistance grows like n to the power d minus 2. Okay. As an exercise, before I finish this, as an exercise, I want you to show what happens when d equal to 1. So in d equal to 1, if you randomly put resistors or remove it, what happens? So that is an exercise for this part. And thank you for these 2 lectures divided into 4 classes. Thanks. So that's where I end my course.